We're back with the Arduino Duo, and for today I got a Baremetal project setup. That means we use our own makefile, linker script, assembly startup file, and the main.c. The project will set up the RAM segments, power management, and the PIOB for blinking the D13 LED. And also I got a debugger here attached, so I will show you what is going on in the RAM segments. So let's get started with the project. Okay, so we are in the project. So first of all, make sure that if you go to the properties, you have selected the right makefile path with the basic commands to build and to clean up. So as you have this here set up, so let's take a look into the linker script before we even do any programming. So the definitions right here for the flash 0 segment, so the beginning, the length, and for the RAM also the beginning and the length. Okay, so right here I got the variables for the stack size and heap size. So those are used to store the variables as you are running your program in RAM. So after this, those definitions, we got the sections to place. So the first one is the text. So right here you got your program commands placed in Flash. After this, I do a align by 4 to have a clean access to the memory. So in the 32-bit architecture, you use accessing by the aligned addresses, so you can access 0, 4, and not 1, 2, 3. So as you do so, you have to collect a variable where you got the text segment finished, so you can begin with placing the data that you got to store next in the RAM. So those are the variable values. And right here also, after the placing, I use the align before, grab the address where I got this finished, so I know the size. Next on, there's a segment called GOT, and this is standing for global offset table. So right here I grab the values for this variable, this variable, and all the others that I need to place the segments in RAM. So also this one, this one, this one, this one, the start of the BSS variable, and so on. And most important here also the last address of the stack, because this will be used in the vectors section, which is in the very beginning of the program. Okay, so after we got the variables for the linker script right here aligned, I also did placing of the ARM attributes, but that is really unnecessary. Okay, so this is actually the end of the flash. So we have to go to the beginning of the RAM address. So to do so, we have to set up the current address to the beginning of the flash right here. Again, this is not necessary to align it by 4 right here, because we got the 0. So we grab the address just to be sure that it is the correct one. We place the data that we have to copy from the RO data segment later in our program. And after that, and also we have to make sure we get the right size of the segment, so we have to calculate it. So the end of the RO data right here minus the beginning of the RO data, place it in RAM, grab the address. You can also calculate the address right here, the size of the data, by adding a variable. And after this we also can add the GOT into the RAM, but this is also not necessary. Next on, we got the section for the BSS. So those are the variables that are set up in a project, but they are undeclared. So they have to be always 0 at the start. So in our program we will zero those segments and grab the end address for the BSS. We can calculate the size like so, and right here I placed a segment just to keep some space, so I can put my own variables into the RAM just to load those segments safely. Next on, we have to place the heap like so. I just copied this section right from the default linker script that is provided by the project you have generated in the Microchip Studio. So this is the same. Just added some addresses here to make sure that they are placed correctly. Okay, so after we place those sections, we are done with the linking. So we have to use the end of the stack variable here. So to do this, we have to add a startup assembly file. And the first thing that we have to start up with, the first vector, is the address that we have to load into the stack pointer. So the end of the stack, like so. Next on is the handler for the reset. So in our case it will be going to the main function, because in the main we got the setting up of the RAM segments. And one thing to notice here, I added 1 to the address of the reset because the linker has to know that it is a function. So you can add a 1 to the address, or you can also declare that it is a thumb function by adding the thumb directive here and right here in the reset. So it will work without adding 1, just having the thumb here and here, or you can not add the thumb right here and just add 1 in here. And if you do both, it also works. So a quick tip. Okay, next on, we got the handlers for the faults. They are just basic go to the start address of the program, nothing really special. And we got right here declared the text segment, so all the functions like so. And we are good to go to the main.c. So let's go in here. So we got some basic includes, and We got some definitions for registers, for the write protection for the power management, for the PIOB, for setting up the power for the PIOB, setting up the PIOB, clearing it, to reset the watchdog, and to write to the vector table offset. And also I declared some addresses for the RAM to keep those variables that you are going to have generated from the GOT section. So the variables that you are creating in the linker script. And right here I got a BSS example data here. Right here are the 0 of BSS, copy the data segment and a delay. So let's first begin with the main. So we copy the addresses from the linker script, set up the vector table offset, and important to make sure that the watchdog is not set up, because if you don't do this, it will reset the microcontroller in a few seconds. So after we got this set up, we are good to go to copy the data from the flash to RAM. So let's take a look here. So in this variable I got calculated the size of the arrow data. So this is calculated in the linker script right here, and this is calculated from the flash segments addresses. So we are doing a while loop in which we will increase the address that we are copying data from, and 2, so we copy the data. This is a variable that holds the RAM address, and this is the data that holds the flash address, and we increase it by 4, so we align it by 4, the addresses. So we copy the arrow data here. After we are done with it, we have to zero the BSS segment. So I calculate here the size of the BSS, and in a while loop I copy 0 to the given address and increment the address by 4, so it is aligned. So after this, I set up the key for the power management. Next on, I set up the PIOB to be set up in the power management. Next on, I write to the write protection of the PIOB, the key, which is this one. After this, I can set up the PIOB 27 as a output by writing to this register and to the enable register, the output and enable, and setting up the PIOB. And this section of the inline assembly does exactly the same as this. That's just for reference. Okay, and next on we got the while loop. So right here I put a string just for testing purposes, so we know that it is all copied to the RAM. And I increase the BSS variable, set up the PIOB, delay some cycles, which I have declared right here. So this is inline assembly for doing nothing command, and it does this command the given amount right here. Clears the LED and waits again. So pretty much simple. So as we got this, we also have to do a proper makefile. So right here I got declared the definition for the tool that I'm using. So this is the default one in Windows, and this is the one that is used by the Microchip Studio. So you don't have any conflicts right here with this as you do so. And this is the flag for the assembly, flags for the C. So we declare the architecture here of the microcontroller, the version of the tool, and the command all does the binary, clean does remove all the files. So first of all we have to compile the assembly file. So we use the tool with the assembly, with the flags, and from the assembly file we have to generate a output file with the same name, just .o. Next on we have to do the same with the main, but this time we have to use the GCC with the C flags. Next on we have to link those two files that we got here generated into a ELF file. So we are using the linker script to link everything together, and with the LD, so linker, we link the startup main using the linker script, and we generate a output, the ELF file. And also it is useful to use the object dump. So from the ELF we generate a list. So let me show you what I mean. So this is the list file, and now we can check if our program is running correctly. So first let's build. So everything is okay. We get the usage here and so on. So let's debug and start. Stop. So we are at the start of the run. So this is the variable from the arrow data right here, and this is already in a run because it's from the previous run, because we did a attach of a debug, and before that the microcontroller was already running, and this is the previous variable of the PSS, so this one. Okay, so let's go back to the disassembly. So let's check where we are at the moment. So the FE, so it will be the start of the main. So now let's set up a breakpoint before doing a delay. So before this function, so let's take a look where we got it placed. So right here we copy the arrow data, we zero the BSS at this address, and next on we got the delay right here, first one. So let's place our breakpoint this address. So we will be at the beginning of the while loop. So let's go back into the disassembly and let's search for 1A8. So right here. Okay, so let's place it maybe even lower or maybe higher, so it will be more safe to use. So let's run it. So we are at the first entry of the while loop. So if we go again running, okay, maybe it wasn't added here. Okay, so now it's added. So let's move a breakpoint right here. So again, it will be increasing. Oh, we didn't hit it. Okay, so it's increased. So the program is running okay with this. So let's just attach the debug again. And let's check if we have the stack pointer set up correctly. So to do this, you have to go to the system registers and search for the stack pointer. So this is the value of the stack pointer currently, as we are at the beginning of the main function. So let's check this with our list file. So at the start we got the address that is supposed to be the end of the stack. So as we see, it is matching. So this is okay. And one thing to mention here, let's take a look at the startup assembly. We got the variable of the end of the stack declared here, but we won't find this variable as we go to the section of the flash 0. So after the arrow data, we have the segment of the GOT, and we are not able to find the end of the stack right here, because the end of the stack is being kept only at the beginning, so right here. And the other variables from the linker script are the ones that we have declared in our main.c as external constants. So all of these are placed right here. Okay, so let's add something up to the program. So instead of the fixed delay, let's add the delay from the variable, the BSS one. So let's make a delay based on the BSS times, for example, 1000, like so. And let's arrange the variable. So if it reaches a certain point, so let's say if it's more than, for example, 5,000 or maybe 50, yeah, something like this. So it will be 0. So okay. So now we can click download. Okay, so now I'm clicking start without debugging. And we got the new program running. So at the start it's linking rapidly. Now it blinks slow. And now it starts again. So everything works as intended. So thanks for watching. Hope you find it useful in your projects. And see you in the next one.